Review of a bunch of rotational stuff. So a lot of these pictures look very similar to things we did early in the year, but now the pulleys have mass, and so we have to look at it a little different. This first one is, let's call it the advanced Atwood machine. So this is the Atwood machine, but now that the pulley has mass, we have to look at it different. And so this is like M2 is the bigger box, and it's above the ground, a height h. M1 is sitting on the ground. Capital M is the mass of the pulley with radius r. And what I do is I kind of just take you through the idea of this is writing F equals ma for the big box. You can see that the weight of the big box is going to be bigger than the tension, and that's going to cause the big box to then accelerate. This is the F equals ma for the small box. The tension's going to win, so it's T1 minus M1G equals M1A. And again, this is just for box 2. This is just for box 1. And then we know that the pulley has to spin, so there must exist a torque. If there does exist a net torque, torque causes I alpha, meaning torque causes the pulley to experience an angular acceleration, which in this case would be to increase its spin rate. It does start at rest. And so torque of it itself is the force times the lever arm times sine of the angle between them. In this case, the angle is 90 degrees. So this is the left string's torque versus the right string's torque. And that's the net torque on the system, and that causes the pulley, which is a 1/2 mr squared, to have some sort of angular acceleration, which we then replace alpha by a over r. And if you look at these three equations, here, here, and here, there are three equations with three variables. This is me just algebraically simplifying the torque equation, but they have three equations, T1, T2, and A, and you could use those three to solve for the acceleration and then go back and find the tensions. Reminder, if you want accelerations, tensions, or alphas, you are likely going to look at torques and forces. The same question, we could look at energy. The energy at the beginning, well, the whole system's going to get energy from M2 losing potential, and then what gains energy? Well, both boxes gain kinetic energy, and since their velocities are the same, you can group them together, or you could write that as separate terms. The pulley gains rotational kinetic energy, and then M1 does in fact gain potential energy. It goes up. The H's are the same. We typically are going to replace omega by v squared over r. We're going to replace I by whatever the pulley is. In this case, it's a disk, 1/2 mr squared. And we take that massive equation and we solve for velocity. Remember, energy finds velocity, or forces finds accelerations and tensions. If we wanted to know things about time, once you found the acceleration, you could go back and figure out the time it would take to drop. You also, once you found velocity or acceleration, you could use this guy. Remember, the v squared equation compares acceleration and velocity. So if you did the top and found acceleration, you could use v squared to find velocity. Or if you did energy to find velocity, you could use the v squared equation to go back and find acceleration. Okay, certainly, if they ask you old school Atwood machine questions and the pulley doesn't have mass, then it's as easy as it's just like M2G minus M1G equals M1 plus M2A. You can write a nice quick system equation and go from there. All right, here's our yo-yo. If they don't say anything, the yo-yo is going to be a disk. The free body diagram now is here. You can't use a dot anymore like we used to, because it matters where on the picture are the forces. So the tension is going to be on the left side, and the weight, the force of gravity, is going to be from the center mass. So if we do F equals ma, we just got this. It's nice and easy. Gravity's down, tension's up. That difference causes the mass to accelerate. And then there are two different torque equations. If we pivot it on the edge, then we have to use the parallaxis theorem. But if the pivot is on the edge, then the torque doesn't cause the tension doesn't cause a torque because it's acting on the pivot. The only torque is due to gravity, and the lever arm is r. So we get this. But if we move the pivot to the edge, we need to use the parallaxis theorem, which says that the new moment of inertia is the original moment of inertia plus md squared. In this case, d is r. It's how far we've moved the pivot from the center. And then, of course, we write alpha as a over r. And if you look at this, we only have one variable. We just have the acceleration. If we put the pivot in the center, then mg doesn't cause the torque. Then we're looking at the tension causing the torque. And so the torque then is just tr. The moment of inertia is the standard 1/2 mr squared because the pivot is in the center. We didn't move it. And then alpha is a over r. And if you do this one, you got to take this equation with this equation and solve because they have two variables, t, the tension, and then the acceleration. Where this one, if you do it this way, the only variable is acceleration, and it's just a one-hit wonder. If you did energy, then it's the loss of potential energy, and then we gain translational kinetic energy or linear kinetic energy or just kinetic energy. And then we also gain rotational kinetic energy as the yo-yo spins. So the yo-yo is moving down and spinning down. And the same thing as before, we can use the v-squared equation to link accelerations with velocities, and we can use kinematics like h equals 1/2 at squared to find the time it would take for the yo-yo to hit the ground. Here's our kind of more advanced ramp question. This does get a little more complicated now that we have a pulley. So again, we're going to look at the forces on M2, and in this case, we are assuming that it's going this direction. So that's the direction I wrote this abstract in. So if it's accelerating in that direction, then M2 is going to beat out T2 and cause M2 to accelerate. Again, this is just looking at box 2. This then is looking at box 1. Tension's pulling up. M1g sine theta is down the ramp. Mu, oh, darn it. That should be a little 1. I didn't notice that. Right there, that's a 1. It's a poorly written 1. That's the friction due to 1. And that's a 1. Oh, man. Both of those should be 1s, of course. Both of those should be 1s. This is then looking at the torque on the pulley. T2, that's the torque caused by T2. That's the torque caused by T1. Thus, then, that's the net torque caused on the system. That torque causes the system to have an alpha. And then you could use these three equations with three variables, T1, T2, and A. You could combine those to then find the acceleration and the tensions. If we wanted to use energy, well, we're losing that energy. M2GH is losing potential energy. We are going to lose the work done by friction. The work done by friction is the force of friction times the distance. The distance this goes up the ramp is h. And then what all gains energy? Well, they both gain kinetic. You can group them together. This is the potential energy that M1 gains, and you got to be careful. M1 slides up the ramp a distance h, but it actually only goes vertically up h sine theta. And then the pulley, of course, gains rotational kinetic energy. And we do our typical song and dance where we replace I by 1/2 mr squared. We replace omega by v over r. H is the height change for M2. H is also the distance M1 moves up the ramp. But h sine theta is actually the vertical height change for M1. And here's the triangle. All right, here's a board just kind of tipping from vertical. So like the wind just barely blows this over and shoom, it falls. If we're looking at an energy perspective, we have to think about the center mass. So the center mass is there, and now the center mass is there. So the energy comes from the loss of potential energy, but it's not the tip of the board, it's the center mass of the board. And so our height change is only L over 2, and it gains this. And since it's pivoted on the end, we're going to use a 1/3 ml squared for our I. So that would be the rotational speed after it's gone from this position to this position. If we're interested in the torque, well, the torque is actually complicated because it changes. At the very beginning, the torque is 0, and at the very end, the torque is at a maximum because the lever arm keeps changing. Well, because the angle keeps changing. But if we wanted to find the torque, the maximum torque or the maximum alpha, that would occur when it's down here. And that would be the force times the lever arm, and those things are perpendicular. And that would just, you could be able to solve that equation to find the maximum alpha of this system. All right, rolling up, rolling down. It's all about converting energy. It looks like this first one I'm going to roll down. So I'm going to start with MGH, and I'm going to give it some kinetic energy, translational kinetic energy, and some rotational kinetic energy. And then I do the same thing. Whether it's a hoop or a disc or a ball, I can replace I by those ideas, and then I can replace omega by V over R. Again, the shape matters. The geometry matters. If it's a hoop, there's a 1. Disc, it's a half. Ball, it's a 2/5. But the mass and radius don't. The mass and the radius, you can see the masses in every one of these terms. And over here, the omega is going to have a r squared in the denominator, and that r squared is going to cancel these r squares. And so the shape, the distribution of mass matters, but not the actual mass or radius itself. If you did forces, then we would look at gravity down the ramp versus friction causes the thing to accelerate. If we looked at torques, it'd be the same thing as above. This is the torque pivoted on the edge, so gravity's causing the torque, or this is torque pivoted at the center. This is where friction would cause the torque. If you move the pivot to the edge, then you got to use the parallel axis theorem to actually find alpha. As a reminder, if there was no friction, then it wouldn't roll. It needs friction to roll. This is like static friction in that the ball or disc or hoop just continues to tip and tip and tip and tip over the surface. Without friction, it would just slide down like a box. And so they definitely have a multiple choice question where they trick you, and you would just delete this term. That would go away if you didn't have friction. It wouldn't be there. So you actually need friction in terms of the roll. A merry-go-round. Merry-go-rounds like our classic. They can ask you for the work done to stop something or to speed something up, and we know that the work done is just that change in kinetic energy. So it might start from rest, it might not, but again, the difference between the kinetic energy at the beginning and the final is then the work done. If you decreased kinetic energy, then you did negative work. If you increased kinetic energy, then you did positive work. And a reminder that sometimes they don't give you omega. Sometimes they give you the frequency. They give you how many revolutions it's doing per second, and you're going to need omega. Or they tell you the period of the merry-go-round. The period, then you can find the frequency, and then the frequency you can find omega. But in this equation, you have to use omega. Again, period is the time it takes. It's in seconds. Frequency, little f, is revolutions per second. And then omega, angular velocity or angular speed, is in radians per second. And again, this equation should make sense because this is how many spins you do in a second, but each spin is 2 pi radians. So you just multiply by 2 pi to figure out how many radians you do per second if you know how many revolutions you do per second. So this also could be a conservation of angular momentum, which is the next unit past rotation, in which it's like a collision, and then of course we conserve angular momentum. 2 more. We got the board and the brick. So this is a stationary thing. This is a brick here. This is a board, and the board is pivoted off center, and we're going to release this thing. So a couple of things. The moment of inertia of this system is the sum of all the parts. And so this is me finding the moment of inertia for the system. This first part is the board. This first part is the brick. It's a point particle. It's an mr squared, where r is the distance it is from the pivot. And then this is the board. The board's pivoted off center, so I have to use the parallel axis theorem. So I have a 1/12 ml squared plus md squared, where d is how far I moved the pivot, and it looks like in this case I moved it L over 4. So this combination is the moment of inertia of the entire system. This is the torque on the system. In this case, both the masses, both the brick's mass and the center mass of the board are both to the left side of the pivot, so their torques are both going to help each other, which is why I added them together. And again, torque is force times lever arm times the sine of the angle between them. And in this case, the angle is 90 degrees, so there's no angle. So there's the torque on the system. That is the system. And then that ratio will cause that system to experience an alpha. And that would be the alpha only at that position, because as they rotate down, their lever arms change, and then the alphas are going to change. Again, the alpha is going to get smaller as the torque gets smaller. If I wanted to find how fast this thing was going to rotate, of course, it's going to be the fastest when it's at the bottom. Then it's a conservation of energy idea. And I have, this is how much the brick's going to lose in potential. This is how much the center of mass of the board is going to lose in potential. And that loss of potential causes then the system to have a rotational energy. Once you found the omega of the board, then if you wanted to find the velocity of the brick or specific parts of the board, then you could do this. Remember, all parts of the board are rotating at the same omega, but they're all moving, meaning velocity, at different, based on how far they are away from the pivot. All right, last one. Now we have kind of a yo-yo, but the yo-yo isn't sliding. It's really just a pulley and then a weight. And so from an energy standpoint, we have the weight's loss of potential that gains kinetic energy of the weight and gains rotational energy for the pulley. If we wanted to look at torques, again, the tension causes the torque. It causes the pulley to experience an alpha. If we want to look at forces, gravity is beating the tension, causing that to accelerate. Again, look at them completely separate. And if you looked at these two equations, they have two variables, tension and acceleration. Solve that system to find the acceleration, plug back in to find the tension. If you wanted to know the time it takes to fall, you can use old school. If you want to know the velocity or the acceleration from each other, you can go back to the v-squared equation. These aren't all of the possible like rotational energy ideas and pictures, but it's a pretty good summary. If you can do a situation like this, a board rotating, a merry-go-round situation, a ball, a hoop, or anything rolling up or down. They do like the conceptual question of who would win down the ramp. Remember, the thing with the smallest moment of inertia will win down the ramp because less energy will go into rotation and more energy can go into translational energy. So if you race these things, the ball will win down the ramp, right? 2/5 is 0.4, which is smaller than 1/2, and then 1/2 is smaller. So it would go ball, would win, then disc, then hoop. Now, if you were rolling something up the ramp and you're asking like who wants to go the highest, well, then it's the thing with the biggest moment of inertia because you want it to have the most energy. And the thing moving, if they're all moving at the same speed, the one thing that has a bigger moment will then have more energy, and that means it'll have more energy to give to MGH. So if these things were racing down the ramp, the ball would win. If you were all rolling them at the same speed and they rolled up a ramp, the hoop will roll the highest up the ramp because it had the most energy to start because it had the biggest eye. So make sure you can understand the differences. And again, both cases, if you want to roll, you have to have friction. And again, pure rolling goes back to this. That's what this means. Pure rolling, V equals omega R, or in this case I wrote it as omega is V over R. Okay, review all these pictures. You should be able to write them in the abstract, and then if I gave you numbers, you should be able to walk through and find those.